Okay, hello everyone. Sorry we're starting a little bit late. It well, I kind of have a day job too. So actually, what we're going to be doing today is continuing our investigation of black holes in the context of our models. We had worked on that last week, made pretty good progress, invented this kind of notion of a causal connection graph. I believe Jonathan has written some code that will allow us to more industrially explore causal connection graphs, and we will get to that in just a moment. But before that, we had a few questions that had been left over from last time. Okay, Jatatan is asking if the hypergraph evolves and branches, new laws of physics develop. Hypothetically, would it affect the theory if experimentalists proved the laws of physics are constant in time and space? Actually, no. Okay, so in the sort of simplest way of thinking about the model, it is a fixed rule that is being applied in all possible ways throughout both the spatial hypergraph and throughout the multi-way graph. So it really is like we imagine physics is. It's a constant rule throughout the universe. Now, there's also this notion of rule space where we imagine looking at all possible rules as rewrites at each step. In that case, it's really a question of what reference frame one's picking, whether one picks, in other words, if one is using the same description to describe things throughout the universe, then once again, if one's using that same description language throughout the universe, then again, one is in a situation where it's the same rule throughout the universe. If one is effectively using a different description language, and there might be different reasons for that, depending on how experiments are done and so on, then maybe there would be a different rule that would be the one that would be the one describing other parts of the universe. But I think in the first approximation, like the kind of, I mean, one of the remarkable things about the universe is it seems to have constant laws that apply throughout the universe. It might not be true, but it seems to be true. I mean, it might not even be true. You know, for all one knows, there could be a varying cosmological constant or a varying Higgs field throughout the universe. It could be the case that, you know, in a different part of the universe, the vacuum expectation value of the Higgs field is different, so the masses of all the particles are different. But that doesn't seem to be the case. It seems to be the case that the whole universe is uniform at that level. By the way, I had a thought, and I'm partly saying this to Jonathan, but I had a thought. So the origin of mass in modern quantum field theory is associated with having a vacuum expectation value of the Higgs particle, of the Higgs field, and then having each particle couple to the Higgs field as it propagates through space, and that's kind of how it picks up a mass in its propagator. And what I kind of realized is that it's that is something that in our interpretation of mass in bulk, so to speak, that is that mass is effectively those causal edges that are being reused in, as opposed to transferring information, sort of fresh causal edges. They're sort of being reused causal edges. And I kind of have this suspicion. Okay, so here's the analogy. When we think about, for example, a photon, and we think about the fact that a photon traveling through a material doesn't travel at the speed of light, that happens because of a refractive index. It happens because the photon is continually getting absorbed and re-emitted with a delay. And so the critical thing is that there is a delay there. So that manifests itself in a more fancy kind of quantum mechanics scattering framework as being a phase retardation. That is, that the incoming wave associated with the particle, the incoming plane wave, is then when it is re-emitted with a phase shift. And so I have this, I'm wondering whether in the life of our causal graph or multi-way causal graph, that might have something to do with this kind of modern ether, which is this Higgs vacuum expectation value. I don't know whether Jonathan has an immediate reaction to that, but
yeah, I mean, that sounds perfectly plausible. I mean, the fact that when there's increased mass, one would kind of expect a phase change, right? Because you know, the increase in mass is referring to an increase in density of causal edge in causal edge flux, which is in turn related to an increase in event density. And if each updating event yields a certain phase shift in the multi-way evolution graph, which we believe to be the case, and that's the basis of the path integral, then there has to be some fairly elementary coupling between causal edge flux density and phase changes. And so I think you might be able to derive some kind of like non-trivial Higgs mechanism coupling that way.
Right. So the question is, one question is how classical and how quantum is the Higgs mechanism really? Because the vacuum expectation value is a classical vacuum expectation value that is constant throughout the universe. Now, for us, for traditional particle physics, that's a big problem because the energy density associated with that vacuum expectation value is huge. And like other, like the vacuum, 0-point vacuum fluctuation energy, has a big gravitational effect. So it would be interesting.
But we know why that miscalculation happens.
Yeah. We understand in our model why that miscalculation, the counting of what's just maintaining space versus what's actually, energy and matter in space. But this is kind of another iteration of that.
That's what I'm saying. We also understand that, don't we? It's just in one case, the calculation is assuming that you're only computing background causal edges with respect to one space-time causal graph, whereas in the other case, it assumes you're counting edges with respect to the whole multi-way causal graph. And so effectively, you're going to be out by a factor of zeta or whatever that number we use for branchial extent is.
Psi. Capital Psi. Yeah. No, but that's a different. Well, that's the issue of. Actually, that's an interesting point. That Psi has a value of about 10 to the 120, as I recall.
Yeah, which is the vacuum expectation failure.
Well, it's also computing with the electron estimated the way we estimated it. It is also the difference between, maybe that's a trivial fact. I think that's a trivial fact. Well, your point is that the vacuum fluctuations are associated with all the branches on the multi-way graph, but yet somehow the true activity, well, it's not obvious to me why that should be the case, why the true activity is kind of a single multi-way branch, but yet the vacuum fluctuations are living on all the multi-way branches. And the fact that the vacuum fluctuations live on all the multi-way branches is fairly clear. The fact that there is order one things that are the visible effect of the energy and matter is not so clear to me. Is it clear to you?
Well, because in general, the causal edge density that you actually observe as a classical entity is on the order of the causal edge density you would see on a single multi-way branch.
That's a somewhat reasonable argument. Yeah, that's a somewhat reasonable argument. But okay, but so how does that relate to the Higgs? For example, here's a good question. If you look at the vacuum expectation value of the Higgs field and you compare it with the vacuum expectation value of the 0-point fluctuations, what's that ratio? I actually don't know. Should know the answer to that. But that's certainly something we can, I vaguely remember 10 to the 60th, but that might be wrong. That's something we can investigate. And that would be if we could get that scaling, that would be very interesting. In other words, the ratio of the Higgs vacuum expectation to the normal ordering 0-point fluctuation in all the quantum fields, because those are two different effects. One is just the classical mysterious origin. In the traditional Higgs mechanism, the origin of the vacuum expectation value of the Higgs field is that weird effective potential for the Higgs particle, right? But there's a sort of a question of whether, if we could have a different way of getting a vacuum expectation value for something that amounts to for a field that couples to particles and that leads to mass, that will be highly interesting. And in particular, one of the things that, that there is, it is sort of a mysterious thing that even though the Higgs field is like an ether, it is still, it's sort of a classical level, it's like an ether, but I guess it's relativistically, it's Lorentz invariant, so that's why it ends up not having some weird effect where particle masses don't satisfy standard relativistic mass increase. Anyway, okay.
Right. But by the way, sorry, I had a slightly different interpretation of Jatatan's question, that in effect, experimentalists, when they probe laws of physics, they're not probing the laws at the micro scale of the individual updating rules. They're probing effective theories at the level of compositions of many, many such rules. And so I thought their question was basically asking, is it possible that that even if the underlying rules are constant, that the effective theories can vary in time? To which I think the answer is yes.
In what way? I mean, by virtue of the experimentalists picking different reference frames, or what?
No, I mean, for instance, if there is if our sort of model of inflationary cosmology is right, and there's global dimension change.
Okay, I see what you're
asking. Then the effective theories are different, even if the micro laws are the same.
I understand what you're saying. So in other words, I mean, particularly with respect to the expansion of the universe, that might be the case.
Exactly.
So,
exactly.
Yeah, that would be very interesting. I mean, we don't know. We keep on kind of dancing around this issue of just how much is the universe, how much of the micro scale compressing while maintaining our perception of fixed scale for us, so to speak. And it is true. I mean, we should think about that. We should think about the question of whether, I mean, by the way, one of the discussions we need to have is really to do a roundup of all the experimental opportunities for the theory, because there are a whole bunch of them. And we just haven't, and I think it's time for us to get on our live stream some astrophysics, cosmology, practical folk, and things like this.
Absolutely.
Because, but yeah, okay, I hadn't understood that, but that's a good point. Let's see. Just let's address, before we jump into black holes, not too literally, I hope. Okay, there's Nolan asking, curious about oligons as dark matter. How do you evade strong constraints on dark matter this light due to de Broglie wavelengths needing to be less than the size of dwarf halos? That's a good question. I mean, from my understanding of the literature, there isn't a fundamental problem above 10 to the minus 20 electron volts. Now, I mean, I think the two constraints that I see here are, one is, how do you make sure they're cold enough? Because if their kinetic energy is too high, they will simply not be captured in the gravity wells of these various of galaxies. And the other thing is the de Broglie wavelength. Okay, so let's look. I'm pretty sure I looked at that. Let me see. Okay, time to probably time to start sharing here. Right, let's go ahead and share screen. Here, let me just do that. And then, okay, I think we're ready to, should be about ready here. Okay, all right, let's take a look at that question. Okay, so the question was, the first question is, what is the de Broglie wavelength of, hold on here, our handy calculator of all such things. Let's see if this works. I doubt I've ever asked this for a de Broglie wavelength of something, let's say 10 to the minus 20 electron volts. That's not a good sign. Oh, 10 to the minus mass, the neutron mass. Why am I being, oh, I see. That's 10 to the minus 20 electron volts of kinetic energy. Right, I need a mass here. So what should I do? Let me just say 10 to the minus 20 electron volts of mass, although that seems kind of, but no, what I really want to do is just convert, okay, 54 billion miles, okay, for that. So that's a small fraction of a light year. So I think that at least at 10 to the minus 20, and I believe that there are a couple of reasons why less than 10 to the minus 20 electron volts starts to get problematic. For example, I think that maybe the de Broglie wavelength gets to be long compared to the size of early density fluctuations, things like that. But I think the more interesting question is about the temperature of these things. And I think the real issue is, when did they decouple in the early universe? And if they decoupled, for example, before inflation, they will be about as stone cold as you can imagine. If they decouple after inflation, it's harder to see how they can be cold enough to have low velocity. The things, it will be good to work this out in more detail and to try and make a good sort of phenomenological study of what oligons might be like at different masses, and how they would show up in the universe. Because I don't think a lot has been done on very light particles, not sort of buying into the fact that they would have only decoupled post-inflation, so to speak. So I mean, something we need to look at. So there's a question from Planumbra: can a singularity exist without an event horizon? That's the whole cosmic censorship question, and we, particularly Jonathan, at least believes, and I agree with him, that there will be an argument that is essentially thermodynamic, or essentially the same kind of argument as the things we were discussing a couple of times ago with, can you construct this very elaborate reference frame, essentially, that avoids the possibility of winding up with that in order to give you a naked singularity, and the claim would be you can't do that in practice, and that therefore you can't have singularities without event horizons. Is that a fair characterization, Jonathan?
Yeah, I think so. Although, as with so many of these things, I suspect there'll be multiple ways of getting to that same answer. Because, for one thing, I think variants of the strong cosmic censorship conjecture are imposed basically just by the requirement that you can foliate the causal network. Because the requirement that there's a consistent foliation of the causal graph in the continuum limit effectively becomes this result of global hyperbolicity, which is related to whether your future sort of null rays are extendable on some Lorentzian manifold. And so effectively, it seems to be the case that as long as you can foliate the causal network in some consistent way, it follows that you must have strong cosmic censorship. And then weak cosmic censorship becomes effectively then a question about whether it's possible to sculpt your causal foliations in such a way as to avoid these singularities. But I suspect that this causal edge thermodynamic argument that Stephen gave will end up being equivalent to that.
Right. So actually, I'm going to just throw out one thing which isn't really relevant to our today's activity, although it might turn out to be. Okay. So I've been thinking about, well, I haven't been thinking as much as I would like to, but I want to think about space tunnels, a modern version of wormholes, so to speak. And the question is, this is the question: is faster than light travel possible in our models? And the issue is, what we know about singularities that can exist in space-time is based on solving Einstein's equations. And the fact is, we get into some pretty funky situations, because even with the Schwarzschild solution, what we're basically saying is we got a solution to the equations, but it's actually not a solution on the full space-time manifold. It's a solution on a manifold that has a point chopped out of it at the center of the Schwarzschild solution. So in a sense, we're saying, well, gosh, if we consider ourselves to be on a different, in a different topological structure of space, then we can get this kind of solution from the Einstein equations. My question is, are we sure that we've inventoried all the kinds of weird things that can happen, particularly when the space comes as a limit of our kind of graphs? And in particular, the kinds of, really weird singularities that one might imagine from topology, and that one might sort of imagine carving out of a continuum space, are different from the ones that I could imagine getting as the limit of our hypergraphs. I don't know if Jonathan has any comment on that.
Yeah, I think that's probably right. So for instance, assuming I understand your concept of a space tunnel, which is basically some portion of a spatial hypergraph that just doesn't happen to correspond to the usual 3+1 dimensional structure. Mm-hmm. Well, as soon as that becomes large enough to be traversable, then it will locally show up as a region of apparently higher dimension, right?
Locally, yes, at its mouth, so to speak.
Yes, right, sure. Because now you have geodesics that can go both along the main space and through the space tunnel. So your geodesic balls are going to have larger volume than they otherwise would. Mm-hmm. And of course, that's not allowable in standard general relativity, because you have a manifold, and the manifold has to have connected components of the same dimension. To do this, we have to have some generalized topological version of general relativity if we really want to understand the continuum limit of those kinds of things. So
I agree that's a good way to think about it, that the mouth of the space tunnel will be higher dimensional, which is something we just never would have seen in general relativity.
Right. Well, it's mathematically forbidden, but yeah, there's no reason to suspect that it's actually forbidden.
Right. Now, the only question is, how would you form a space tunnel? In other words, there might be space tunnels left over. It's different from a wormhole, because a wormhole exists in 3+1 dimensional space-time. So, the question is, could space tunnels be left over from the early universe, for example?
Right. Although space tunnels will presumably manifest as wormholes, in the sense that if you constructed a space tunnel in the hypergraph, you would presumably also see a tunnel in the causal network. Because if information can traverse,
sure, then sure. Okay, so what does it mean?
There will be
higher dimensional in the spatial graph, and so what is that implication of that for the causal graph? So causal edges can then go through. Okay, so causal edges can go through the space tunnel. That's the whole point. If causal edges couldn't go through the space tunnel, then there's no point in saying it's a tunnel.
Right, exactly. So it's also going to show up, unsurprisingly, as a higher dimensional region of the causal graph.
Yes. What can we say about the energy associated with a space tunnel? So, I mean, what can we say about the mouth of the space tunnel? Because I think that there will be some constraints on what's possible just by virtue of, one question is, can a space tunnel, it's the same question as for a wormhole, can a space tunnel be persistent? What does it take? Is that inconsistent with, and I think the answer is, all we know, okay, so the point is that our derivation of the Einstein equations involves fixed dimension. Right? So this is saying, imagine that we have something where there isn't just one single, all we know is that the derivation of the Einstein equations requires that we be in a finite dimension. The question of whether we could have two different dimensions is not, I think, answered by that derivation. But what it looks like in this, around the mouth of the space tunnel, so to speak, is very unclear to me.
Right. I mean, well, the derivation of Einstein's equation simply doesn't hold in the vicinity of the mouth.
Because
the derivation effectively assumes that in the limits as the causal network becomes infinite, the dimension kind of smooths out. But here you're going to get some kind of dimension discontinuity.
Right. Well, so in particular, if we look at the volume of geodesic balls near the mouth of the space tunnel, then it will be
their scaling exponents will be different to the volumes to those of the geodesic balls in the vicinity.
Right, but in particular, what will probably happen if it is let's say it's a one-dimensional space tunnel, right? What will happen is that as you go around the geodesic ball, so to speak, as you go around the directions of the geodesic ball, you'll end up with different growth rates in different directions. In other words, normally for curvature, you expect that the Ricci tensor describes different growth rates at the curvature level for the geodesic ball, but this is saying you would get different growth rates at the dimension level for the geodesic ball.
Right. It says that there's some kind of dimension tensor that you're then projecting.
Right. So what we need, we need a dimension tensor basically, and what we need is some examples of spatial graphs for which the dimension tensor is not, because I mean, your average run-of-the-mill, graph, the dimension tensor, or let's even talk about how that would work. I mean, so what you're saying is you start from a given node in the causal graph and you're looking at the geodesic ball and you're asking, I mean, it's just measuring growth rates along tubes as opposed to in a sphere. That's effectively what you're doing. In different directions, you're measuring it's just like measuring, it's what we will ultimately do to measure the Ricci tensor, is you're measuring the growth rate of the number of points that exist in a growing tube in a particular direction.
Right. So the most naive way you could compute it is, so in the same way as to compute the Ricci curvature, you're basically saying assume locally fixed dimension, and then do this expansion of the volume of the geodesic ball. If we did the same thing, we say assume locally fixed curvature, and then expand in the exponent. Then that would give us a computation of the dimension tensor.
The other thing we could do is, I'm not sure that we've really looked at this is something we have not properly looked at is isotropy, basically. I mean, this is a question, you know, AKA, what is the level, is there isotropy of dimension around a given point? And I think we don't know the answer to that. And I think that's something that we could look at. And I think we probably haven't seen that very much because we've been looking at initial conditions that are, in a sense, very isotropic.
Right. I mean, so certainly in the causal graph, if you have spatial dimension change, there is not isotropy of dimension.
For sure. But I think, you know, I'm asking, even in the spatial graph, does it have to be isotropic, spatially isotropic, with respect to dimension? You know, there's a question here from Brian asking, what would the geodesics look like on the back side of the space tunnel if you were to walk around the mouth without entering the tunnel? And then would the mouth of the tunnel be multidimensional and be accessible from all directions? You know, our powers of, I'm bad at visualizing things in three-dimensional space. This is asking for visualizing things in variable dimensional space. Let me think about that. So the geodesics, there will certainly be geodesics that do not enter the space tunnel. I think it's a question of you know, there'll be some, how would this work? You know, I think basically around a point, some geodesics will just go and do their merry thing as if there was no space tunnel, and some geodesics will enter the space tunnel, so to speak. So, I mean, roughly what we're looking at here, let me see. So let's do something very naive. I don't know why I'm making a vector plot. Anybody know how a dipole works? Can I make a dipole? Anybody immediately know the equation for a dipole without me having to try to compute it? Jonathan, this is where we need a, who can tell us what I'm looking for is something where we have, oh, is this a dipole field? This maybe is a dipole field. Let's see if this is a dipole field, just for the sake of having, so let's say charge 1 and charge -1 here. Okay, not great. Okay, so what I'm imagining here, and this is a really very bad example of this. Actually, it's a very, very bad example. I mean, what we need is something where we're seeing effectively, I mean, this is obviously just a two-dimensional thing, but I'm just trying to get some sense of what it would look like close to the, you know, we'll have a bunch of things that are just essentially radial, what appear to be sort of, you know, in what we thought was 4 pi steradians, so to speak, there will be essentially a monopole-like string hanging out of that, if that made any sense. Like in the, you know, when we try and put magnetic monopoles into a standard, I mean, actually an interesting question, what is the analogy with magnetic monopoles? Because magnetic monopoles, in the usual way they're set up, have to have a string, basically, in which instead of connecting to another magnetic monopole by having something like, you know, standard inverse square law, the magnetic monopoles have to be connected by some kind of string where the magnetic field lines are compressed into this one-dimensional thing. And I'm kind of thinking that might be maybe what this would somewhat appear like. Anyway, I mean, I think the thing that would be lovely to have is, you know, a playground where we can see what is, you know, how do we make variable dimensional stuff? You know, and I mean, so here's a very naive thing we could do. We could take a grid graph with, let's say, we take, I mean, we clearly could do something where we glue, you know, there's a three-dimensional grid graph. It's kind of silly, though. I mean, clearly we can glue a bunch of planes effectively onto the edge of that grid graph. You know, it's got a bunch of streamers coming off it that are two-dimensional, but I don't think that's the interesting way to think about this. All right, anyway, this is an interesting challenge. Okay, let's look at a couple more questions here, and then we're going to jump into black hole searching. There's a question here. What is the equivalence of black hole-like singularities in multi-way hypergraphs, Adinkras, Feynman diagrams, and relationship to ER equals EPR? That is a big pile of different kinds of things here. First of all, Feynman diagrams don't have anything like black hole singularities. Feynman diagrams are creatures of quantum field theory, and black hole singularities are creatures of classical general relativity. And the only thing one sees is, like in sort of a simple version of Hawking radiation, one sees a Feynman diagram where a particle in the Feynman diagram, like a member of a virtual particle pair, just sort of gets chopped off because it's sort of in the space-time diagram, it falls through the event horizon. I don't know, Jonathan, do you want to say something about ER equals EPR?
We can, although we do have a Q&A answer about this.
Okay, go look at the Q&A answer. That's our first step. Let's pull up the Q&A answer, and that way we can at least have something on the screen.
But yes, basically the ER equals EPR conjecture is quite straightforward to kind of validate in the context of our models, because it's basically just saying that the natural distance measure on branch yield space is entanglement entropy, which we know in certain cases because of the properties of the Fubini-Studi metric.
That was more complicated than I think it needs to be, but I think the conclusion is correct. I see. You're talking about it in terms of really talking about the Bekenstein-Hawking entropy.
Yes, right. So there's a hand-wavy explanation of ER equals EPR, which is basically just saying wormholes and entanglements are kind of the same thing, which is sort of trivial in our models because it's just they're two different kinds of causal connection, one in the space-time causal graph, one in the multi-way causal graph. But there's a more interesting and deep version of the same conjecture, which says that, as I say here, that the Bekenstein-Hawking entropy and the entanglement entropy are the same if you have a pair of entangled black holes. And that turns out to be a much more non-trivial statement about the geometry of branch yield space that seems to be true, at least in some cases of our models.
Right. The other coming attraction is, are particles like electrons actually black holes? That's another coming attraction that we need to look at. Not directly related to this, but of sort of the same character of a connection between what seems to be a very gravitation-oriented thing with something completely different. Okay, right, Brian is asking, did the glossary get published? And I'm embarrassed to say that the answer is no, and that's a good poke for us to get it done. Consider us appropriately poked. Maybe we'll work on that today. The question about the models imply that the universe is finite. Actually, that's something for which we should have a Q&A answer. The answer is yes, but big.
And observationally infinite, potentially.
In the sense that by the time your light signal could have reached the edge, the edge would have moved, so to speak.
Exactly.
Okay, there's one that's aimed at you from Salim, I think. Are reference frames in a combinatorial rule space like entanglement reference frames equal to the infinite equivalent particle paths of Feynman diagrams? Relationship between Higgs and Planck space time steps.
That is beyond my pay grade. Do you understand this question?
Not really. I think we need it simplified for us, please.
Yeah, Salim Hugh, if you can walk us through exactly what you're asking, we can try and answer. But this is too complicated for us to understand as it's currently phrased.
Okay. So let's see, a question from Ben here. Computing Lie algebras, I need to approximate the Campbell-Baker-Hausdorff formula, and Dinkin's summation is quite dirty, he says. How to use non-commutative multiply? Is there a worked example? Notebook. I don't know offhand. Maybe somebody can go and try and find out. Maybe Jose would know that. I do not know. I think we need to smarten up our treatment of Lie groups. I think we're now motivated by thinking about these models because, this whole question about how do we, I see, you're asking I don't actually know whether there's a way of using Baker-Campbell-Hausdorff, exponentiation of operator products and so on, the expansion of the exponential of an operator product. That's an interesting possibility as a way to think about approximating a Lie group. And I don't know. I mean, it's one of our important coming attractions. We think we have some intuition for the way that spatial hypergraphs can limit to manifolds, how things limit to Lie groups, and which are themselves, defined manifolds too. That's an interesting question, and we need to work on that.
Someone on the Mathematica Stack Exchange does seem to have used non-commutative multiply to implement the Baker-Campbell-Hausdorff formula.
Okay, maybe somebody can post that.
Okay. Hopefully, I should have sent the link.
Okay, the question here, we should get to our main event here very soon, but are white holes forbidden? I'm now confused. I mean, I remember thinking about white holes when I was a kid and being, and then being very confused later on about what on earth a white hole really was supposed to be. I mean, a white hole might be a time-reversed black hole, but I don't even know what that means in the modern world of Hawking radiation and so on. I mean, you could imagine is there a solution to the Einstein equations where there is a similar, removal of a point in which there's, why can't you have the time-reversed version of a black hole?
You can, you absolutely can. And I mean, that's what white holes are at some level.
Okay, so the question then is being asked of us, can those exist in our models?
Well, suppose you constructed one of your space tunnels, and you then consider its extent in the causal graph. So at the opening of the space tunnel, right, all of the causal edges are pointed inwards, but at the other mouth, all of the causal edges are pointed outwards.
So you're saying that it could be the case that the two ends of the space tunnel, I mean, I guess this happens in wormholes as well. I mean, the ends of the space tunnel are a bit like a black hole and a white hole.
Right. I mean, there are many different kinds of wormhole solutions that are permitted by the Einstein field equation. Some of them are symmetric and some of them are asymmetric. And so this would be an example of an asymmetric solution.
Well, but you're saying where there's a bunch of, so one issue is in a black hole, and this is what we're about to get to today, energy is being, sort of spirited away in this causally disconnected region that is the black hole. And, causal edges are going into that causally disconnected region, right? In the white hole case, what's being said, and I'm not sure that's possible with local rules, well, maybe it is that what we're saying is that energy that was in something causally disconnected is suddenly causally connecting itself again.
So imagine you have a causal graph that just has, in the middle of it, so to speak, there's just a single path, and then for every event on that path, there are two causal edges pointing outwards. So now that's a region of space-time for which information can emerge, but it can't go in.
Wait a minute. Sorry, I lost that. Could you say that again?
So in the same way as we think of a black hole as being some structure in the causal graph where there are just causal edges pointing inwards.
Yes.
Imagine you had a path in the causal graph where there were, along every event, there were just two causal edges pointing outwards, for instance. That would be a region of space-time in which information can come out but can't go in.
In which for you're going along the causal graph.
Yeah.
And
like I say, I think the simplest model is you have a single path. You consider some path in the causal graph where for every event, there's a pair of causal edges emerging.
Okay, so there's a pair. So in this case, we would take each one of these points and we would say, so it'd be something like table, something like I goes to I plus 1, and also I goes to, let's say I plus 100 or something. And then we would get I going to 10, flatten that, and get a graph.
Right. Okay. That would only, yeah.
So you're saying, is that what you're imagining?
Well, I kind of thought two edges coming out, but that also illustrates the same idea.
This does have two edges coming out of each one, right?
No, there's a path with only one edge coming out of the event on either side.
Wait a minute. So what would you like this to do?
So that should also be, I goes to I plus 200.
Okay.
Right. So now you have a path with, as I say,
Oh,
for every
things
event
being spun off, but I don't see why. Okay, so let's do a layered graph plot.
So then that's the time reversed analog of the ordinary black hole case, and so it corresponds to a region of space-time in which information can come out but can't go in.
Okay. Fair enough. So this is, so here.
You see what I mean, right? If you did the reverse graph of this, then you would get, then that would look like branch pair convergence.
Wait a minute. By the way, why are we getting all this clicking? I don't know what somebody has a source of clicks here.
Oh, sorry, my audio setup might be kind of bad.
It sounds just fine, except for the fact that it's clicking every so often. Okay, so now we've got something where, let me try to understand this, where you're saying that these are causal edges that are finding their way into this black hole-like thing.
Yep.
From the rest of the universe.
Right. So this is just this is simply the statement that a white hole is a time-reversed black hole.
In what sense is this creating energy from nothing? I mean, it is, but which is not objectionable. Actually, Max, welcome back, Max, is pointing out that we could search for white holes at the same time as black holes, since the code is essentially the same.
Yeah, that's what I'm saying. One is a reverse graph of the other.
Right. Okay. All right. Let's get to yeah, Ben is saying in response to some previous thing that you need Penrose diagrams, not Feynman diagrams, for sure. And an interesting question is, to what extent are Penrose diagrams and Feynman diagrams, which normally have nothing to do with each other, to what extent in our setup do they have a relationship? Because one of them is representing causal edges, and insofar as we believe that things like branch pairs are associated with virtual particle pairs, I mean, although to be clear, what we imagine a particle is a big, complicated mess of edges. But what we're able to see in these graphs at this level is just what's happening at individual edges. And it may be the case that that is a good proxy for what happens for this big, fluffy particle that's a whole electron with, 10 to the 20, 10 to the 30 edges in it.
Right. Feynman diagrams are multi-way Penrose diagrams.
Well, that's an interesting, I'm going to write that down as an aphorism. Are the multi-way analog of Penrose diagrams. Let's see how much we believe that for a second. Actually, that's not that far away.
Right. There's some slight difference in how conformal scaling works, but other than that, they're the same.
Well, let's go through what that means. A Feynman diagram is a representation of causal effects associated with the quantum field theory, in a quantum field theory. In other words, you can think about a Feynman diagram as being, when we take your average, boy, where do I get a Feynman diagram from? Help. I've got to have one. I'm sure I have some in the NKS book. Nothing else. No way that there's some. I just want an average Feynman diagram. Here we go. There are some good average Feynman diagrams. Okay, so how do we think about this? Well, we can think about this as a causal graph, I suppose.
Right,
in
but
which
it's a multi-way causal graph.
A piece of a multi-way causal, a piece of the multi-way graph, because it is, in a sense, you're arguing a very interesting claim that, clearly with Feynman diagrams, any given process, there are many Feynman diagrams, like this particular process, this is Compton scattering. Any given process, there might be a whole collection of possible Feynman diagrams that represent that process. And you are arguing effectively that those are essentially pictures of possible branches of the multi-way causal graph.
Right. Yeah, branches in the sense of bundles of causal edges corresponding to single evolution branches.
Yes, that each one of these is potentially a single branch of evolution in the multi-way graph, but this is its shadow in the multi-way causal graph. And so then the argument would be that if you take one of these things, and the domain of Penrose diagrams is curved spaces and things, which is not the domain of Feynman diagrams. Different.
Although, QFT in curved spacetime also uses Feynman diagrams. Admittedly,
sure it does, but it just has different propagators. That's the only change. Right. In other words, the spacetime is treated as a background, and I don't know. Maybe I'm just out of date because but when you draw, the only place where you're doing something is in things like Hawking radiation, where essentially one of these lines just says, "Oops, went over the event horizon. It's gone," and that's pretty much the only thing I think. Salim is pointing out if you invert the entire multi-way graph, then all black holes would turn into white holes. I think that's true. So Here's an interesting question. So, what is the relationship of CPT invariance to white holes? So CPT invariance would imply that, if general relativity, or if the gravitation layer, so to speak, is CPT invariant, then there should exist black holes just as there exist white holes, just as there exist black holes. But it's not at all obvious that the full solutions, there can perfectly well be essentially spontaneous symmetry breaking in the solutions that get picked out for the universe. So it's not totally obvious that you would have to have that invariance for the actual
here's a question that I think is really interesting, which is, what is a white qubit?
Yeah, okay, that's an interesting question. Okay.
Because that effectively allows us to answer the question of what happens with time-reversed measurement, which is something that has been attempted to be addressed, but has not been successfully addressed in conventional quantum mechanics.
Well, time-reversed measurement, yeah, right. Time-reversed measurement is a mess.
Yeah, exactly.
Time reversal of measurement is the same issue as the story of time reversal in the second law of thermodynamics.
Right, exactly.
And okay, so let's think about that for a second. So,
because a quote unquote white qubit would be one where decoherence works in the opposite direction, where it's recohering.
Right. I think white qubits live in white holes, so to speak. In other words, I think you have to have. My claim would be that because the arrow of time, that you don't get white qubits because effectively the arrow of time, there are many arrows of time, the cosmological arrow of time, the local thermodynamic arrow of time, the sort of psychological arrow of time. In our model, all those arrows of time are aligned. And my claim would be that to get a white qubit, you have to reverse one of those arrows of time, which I claim you can't do because you're kind of stuck with the whole universe operating in the cosmological arrow of time that it has, which then becomes the thermodynamic arrow of time, which then feeds itself into the blackness or whiteness of qubits.
Right. Or to put it another way, it's the analog of saying that just as saying you can't have negative mass in conventional general relativity is what effectively says white holes should be unobservable. There's an analogous claim that holds in the multi-way causal graph that tells you why qubits always decohere rather than recohering.
Let me understand that. So negative mass is a different issue, right? So in our
the statement that you get causal edges that can get trapped in a region of the causal network, but you don't get the sort of time reversed phenomenon, is related to the fact that gravity is a purely attractive force.
Let me understand that claim. So negative mass would be associated with, let's see, negative mass, I think, we were talking about the retardation of causal edges. isn't negative mass the acceleration of causal edges?
Right. Which would happen if your background causal edge density is somehow lower than the average causal edge density for the universe.
Right, but I mean this requires advanced as opposed to retarded causal edges, and
right,
you're saying that can happen if you are in a region, if you're in a kind of a vacuum of the vacuum, so to speak.
Right, a sub-vacuum. But that wasn't the point I was trying to make. The point I was trying to make was that the fact that you observe.
Here's a very critical point. Okay, uniqueness of the vacuum. Is the vacuum unique? In a sense, in our theory, uniqueness of the vacuum is a statement of equilibrium.
Right, it's necessary for the weak ergodicity hypothesis that we need.
Well, in our models, uniqueness of the vacuum is like uniqueness of the equilibrium state in thermodynamics. It's the direct analog of the uniqueness of the is the direct analog of the uniqueness of the equilibrium state in thermodynamics. So that actually suggests an interesting thing too, because when there is an equilibrium state in thermodynamics, okay, so when isn't there a unique equilibrium state in thermodynamics? Answer: when there's a phase transition. So then the question for us is there only one phase of our vacuum? Right. In other words, is there only one equilibrium as a function of, well, what's the analog of temperature and pressure?
I mean, so obviously the answer to this would be no in the proximity of a space tunnel.
Indeed. Indeed. And it might also be no in an early universe, the little bubble universe that happens.
Right. But sorry, the point I was trying to make was a different one. I mean, so the fact that black holes are observable but white holes are not, as far as we know, is presumed to be related to the fact that there is this asymmetry in the gravitational interaction that makes it purely attractive. Right.
Yeah, I understand, but
so then the statement that qubits decohere but are not observed to recohere is a purely thermodynamic argument. And so if there is this correspondence between the multi-way causal graph and the underlying causal graph, that implies that the attractiveness of gravitation should also be derivable by purely thermodynamic arguments, which we kind of
right. Let's look at that. Let's look at that. Hold on one second. So then the question is the positivity of mass purely thermodynamic, so to speak? Okay, so positivity of mass essentially derivable thermodynamically. All right, what does it mean? So I think that's related to this uniqueness of the vacuum issue, because I think that what's being said there is that you don't get to have more vacuum than vacuum, so to speak, somehow, right? Because in order to have negative mass, what you're saying is I want less stuff around than exists in the vacuum. In a first approximation.
Yeah, I understand.
Right, so I would claim, okay, the question is, is this like the colder body, hotter body story of what is the analog of temperature for our vacuum? It must be, the analog of temperature must be things about causal edges.
Yeah, average flux of causal edges through time-like hypersurfaces, or average flux density.
Is the analog of temperature?
Well, it's directly related to temperature.
So the claim would be, okay, so for our vacuum, temperature, and I'm sure this is true in relativistic thermodynamics, temperature is related to to energy density. Pressure is related to momentum density. So what we're saying here is the standard temperature pressure story is, does there exist a different solution, a different stationary solution effectively to our, in other words, given a particular underlying rule. Let me give you an analogy. In cellular automata, it's pretty common to find same underlying rule, different, just different possible structures, if that makes sense. So let's take an example of that.
Right. And so the analogous case here would be asking if the associated equation of state for the vacuum is non-convex.
You could think about it that way.
Because surely if it's the condition where you have multiple temperature and pressure values consistent with the energy and momentum density values is exactly the case where the equation of state is non-convex.
I have to think about that for a second about convexity. I'm not sure why. I mean, the analogy that I'm imagining, let me just pull up an example here.
Well, because otherwise if it's convex, then there's only a single, then the curve doesn't overlap with itself, so to speak. There's only a single solution for each pair.
Convex is a function of what?
Wait, I mean, as in temperature is a function of energy, pressure is a function of momentum.
I don't think that's I mean, if you want a coexistence curve in a phase diagram, there is a condition, there's a convexity condition for that, but I'm not sure it's the one you're thinking of here. Look, I'm just picking out an analogy. Let me just try and find an analog here. I think there was a good example. Let's see. I think there's some examples here where well, those are just a single rule and different periodic initial conditions, but there are examples here where, yeah, I mean, that's a good example there. Just to pull it. Can I pull that over? Does that work? Help, what's happening here? Oh my gosh, it pulls the whole page over. That's really useless. I thought we don't yet have click to copy for all the pictures in NKS, but we will. But I mean, so this is the analogy. So this is a case where same rule, but different, it's a self-maintaining structure, but which has different properties, so to speak. So in other words, do there exist multiple equilibrium states? And we have no idea. In a word, we have absolutely no idea. Most likely, one of them is going to be metastable. Can we? Okay, is one of them always metastable? Probably the answer is yes, because one of them will have higher. Okay, but this is coming back to this question of deriving positivity of mass. Okay. Well, the claim has to be about this metastability thing, that the lowest. Okay, the claim would have to be that the version of space that maintains itself with the lowest number of causal edges is the most stable, is the true vacuum. In other words, there could exist, because it could be the case that our vacuum is using twice as many causal edges as you really need to maintain the structure of space. See what I'm saying?
Right.
And that if that's the case, then you could say, oh, let me make a vacuum cleaner. Yes. Can you create a vacuum cleaner, so to speak? That will take your vacuum and make it into the lower, that our vacuum is the higher number of causal edges vacuum, but there is in fact a lower causal edges vacuum that can operate with this rule. So that's an
Right.
interesting question, whether there can be multiple. I mean, what we should do, like with cellular automata, we found that by virtue of, I mean, in fact, there are initial conditions of positive measure that have distinct outcomes, right? That wouldn't be obvious. It might be just measure zero. But there are ones of positive measure that have distinct outcomes. I mean, a good example of that is what happens in these ones where is it? There's probably one here. Yeah, this guy. Actually, the more extreme version of that guy is, let's see if we have one here. Oh, come on. Yeah, I mean, basically, this thing will either end up with white, a bunch of right-moving white stripes or a bunch of back-moving, left-moving black stripes, depending on the initial density, and both have positive measure. So, I mean, this whole question about the uniqueness of the vacuum is a giant can of worms in axiomatic quantum field theory, with a complete inability to prove anything about it. And for example, the QCD vacuum is certainly complicated and definitely not obviously unique. So this is a really interesting question. Is the vacuum? What's that?
I don't disagree with any of this, but you do see my point, right? That this is only a specific instance of a more general question.
All right. What's the more general question?
What about the uniqueness of the vacuum in the multi-way causal graph? The question of why entanglements propagate from the system that's being observed out to the environment and not the other way around. Why do qubits decohere and not recohere? It's the same. It's the more general case of the same question.
So you're saying, okay, so I mean, you're claiming general case is in the multi-way causal graph. You're saying what I'm asking about is the causal graph, and
right.
What you want to ask about is the multi-way causal graph.
Right.
So the intuition in the causal graph is that there is a vacuum and there's no cleaner vacuum. And you're saying in the multi-way causal graph, the same thing is true. There's no way. What would you need? I'm sorry, to have the recohering qubits, you would need something where there is effectively a
well, where you have two different vacuum phases, where you have two environments where one is more entangled than the other, but both are consistent with vacuum states.
Yeah.
Which basically means that you have two different environmentally induced eigenbases, selection eigenbases.
Okay, let's walk through what that would mean. So what you're saying is that in the normal course of events, there is a certain rate of environmental measurement, so to speak. There's a certain inexorable rate at which the environment impinges on your qubit. And that rate is determined by the structure of the multi-way causal graph, which in turn is related to the structure of, well, quantum space, so to speak, branch Hill space, which we don't know a hell of a lot about, realistically. I mean, space-time, we know a reasonable amount about. We know how many dimensions it has. We know, etc. But branch Hill space, we actually don't know very much about. So this is the statement that there is only one equilibrium branch Hill space, right? So this is a statement of uniqueness of equilibrium branch Hill space.
Well, equilibrium in the sense of causal edge density in the branch Hill causal graph.
Yes, that's what I mean. I mean, but that means that in the look, what this would be is a place where quantum energy is a region of quantum space in which, or branch Hill space, in which there is sort of a hole, in which there's a different level of ambient it's kind of a super selection sector where the vacuum energy is different.
Yeah, as I say, it's a different Ein selection basis.
I'm just trying to understand it in terms that I understand. So, I mean, this would be okay, so the analog would be a super selection sector where the vacuum energy is different. Okay, so I'll tell you how that could happen. I mean, so basically, oh, there's a spelling word for us. Normally, in quantum field theory, right, you have vacuum fluctuations of every particle type. Could you have a situation in which, for whatever reason, certain particle types simply couldn't exist in that area? You know, in other words, there are no, say, there are no vacuum fluctuations associated with particle type particles of type X.
Right.
In a particular region.
I know that you disagree with me on the interpretation of the Casimir effect, that you claim it's a bulk QFT thing. But my understanding was that there's an interpretation of the Casimir effect in terms of exactly this question.
Well, no, the Casimir effect is that, you know, you have a box of a certain size, and within that box, no mode whose wavelength is larger than the size of the box can exist.
Right, right. So there's a generalized Casimir effect in which you basically have a region of the spatial hypergraph which by its construction doesn't permit topological obstructions of a certain size, of a certain type.
Yeah, that could happen. Okay, let's think about that for a second. Okay, so all right, so this is, can you make a generalized Casimir effect where some external constraint determines the which vacuum fluctuations can exist? Right. So in other words, it's like the habitat of you know, because in the standard Casimir effect, the only thing you're doing, well, it depends on the boundary conditions for a particular field. So for a particular field, if the walls of the Casimir box are transparent to field X, then field X does not have a Casimir effect. So that would be a way of doing this. You have a box, e.g., have a box that is transparent to particle A, but not B. Okay, so if you do that, then that will effectively give you, you know, it will affect the zero of energy for particle A versus B, because by removing the far infrared degrees of freedom, the long wavelength degrees of freedom, you're effectively putting a floor on the energy. So how does that relate to what we're talking about here? So we're saying here that, yeah, I mean, so this statement could be done graph theoretically as some region of the graph, you know, simply you have managed to eschew some kind of non-planarity in some region of the graph, and you can maintain a lack of non-planarity.
Right. It's a second order obstruction, right? It's an obstruction to, it's a topological obstruction to topological obstructions.
Yes.
Which is a perfectly well-defined concept.
Right. Okay. So e.g., graph theoretically, this would be obstruction to the presence of topological, obstructions.
Right.
Fair enough. So that yeah, this is interesting. So just to walk this through for one more moment. So the claim would be, okay, so let's imagine we had this more vacuum than vacuum, so to speak. Okay, the cleaned vacuum. And suddenly a bubble of cleaned vacuum could pop up inside our vacuum. Okay? That bubble of cleaned vacuum would have negative mass, right? Because it has a lower density of causal edges. It has, that's a bubble of negative mass, basically. So in a sense, what all we're saying here is that a negative mass object, I mean, this is kind of an obvious fact, a negative mass, negative energy object is an object which has for which the density of causal edges is lower than usual. And the point is that's usually hard to achieve for essentially thermodynamic reasons. That is, this is like, third law of thermodynamics territory, where you're saying, okay, so the question is, can there be, okay, next question is, can you create a vacuum refrigerator? Which effectively reduces the energy of one region, which effectively reduces the energy density of one region of vacuum. So the question is there in favor of another? So that's like a heat engine operating in the vacuum. So you've got to be able to have something where you are progressively moving. And so one question is, what does it take to, I mean, I bet there are pure thermodynamic arguments here that one could make. I mean, the thing is that refrigerators require the expenditure of energy. Yeah, I mean, this is the question. Can you make a refrigerator, basically, for the vacuum? That must be a thing. I mean, in black hole thermodynamics, that has certainly been thought about. What is the analog of a refrigerator in black hole thermodynamics?
I'm not convinced I understand the question.
Okay, so
I understand I understand your notion of a vacuum refrigerator, and I think I understand black hole thermodynamics, but I don't understand the statement that they've been considered in that context.
Well, I don't know whether they have, but I mean, the idea would be, can you reduce the temperature of a black hole?
Yeah, I understand, but I mean, how would you do that? That's what I've never seen any construction to that effect.
Well, how would you do it? And the fact that you can't do it might be a sign of something.
Well, right? The fact that you can't do it is precisely the fact that gravity is time asymmetric.
Yeah. Well, we're coming back to the same.
It would require you to be able to reverse the curvature at the event horizon of a black hole to a sufficient extent as to reduce the Hawking radiation, which you can't do because mass is positive, which was kind of my point to begin with.
Right, but the thing is, because we actually have a notion of, we have a definite notion of negative mass here. The negative mass, the notion of negative mass is fewer causal edges than are normally present to maintain space-time.
Right. But then, in order to define the notion of a space-time metric, you need to have sufficiently many causal edges that you have stable space-time.
Indeed, you do.
So when you reduce the number of causal edges to a faux sub-vacuum state, it doesn't seem at all obvious to me that you could associate that with a sufficiently well-defined region of volume, a sufficiently well-defined volume element to be able to say that the energy density were lower than the actual vacuum state.
Okay, the question is this: given the volume of geodesic balls, okay, the growth, what we care about is growth rates of geodesic balls. The actual geodesic ball, this is the point, that the energy is in some first approximation the constant, the multiplicative factor in front of all these growth rates.
Yes.
And so the question is, it's like the cellular automaton case. Is there we've got a happily evolving hypergraph, for example. The question is, for a given rule, are there two different subspaces, that could be distinguished by some super selection sector or however you want to describe it, two different subspaces that both correspond to valid I mean, okay, there's a couple of different
Yeah,
decisions.
no, I understand. So yeah, so you'd have two regions of the causal graph that are both valid solutions to the Einstein field equations in the sense that they are causal invariant, asymptotic dimensionality preserving, all of that stuff. But
Yes.
they just happen to have two different levels of background causal edge density. And my point is that at the boundary between those two regions, you're going to have a discontinuity, which is going to break the weak ergodicity hypotheses in exactly the same way as it does for the space tunnel, because the space tunnel is an example of this. And so my point is, you don't have a well-defined notion of a metric in that vicinity.
Yeah, I agree. There's an issue with that. So let's just think about that for a second. I mean, the
And so
transition between what happens in cellular automata in these cases, the answer is what tends to happen is there's a domain wall. Right. So in other words, in general, between two phases, there will be a domain wall. Now, does the domain wall survive, or does the domain wall sort of self-destruct? Well, that's a detailed question about the phases. So now the question is, what you're asking is, can you define a metric in the domain wall?
Right, which in the space-time case is no. If you want it to be a space-time metric, you can't.
Why?
Because weak ergodicity fails.
Well, our derivation of deriving the metric fails. I mean, the question is it is a domain wall a continuum thing? And the answer is not really.
Right.
The continuum hypothesis, so to speak, not the continuum. Never mind. That's the wrong sense of continuum hypothesis. But the notion of a continuum, of having a continuum limit, would fail at the domain wall.
Right. And so my point is that a space-time metric being a continuous object, therefore cannot exist.
Yeah, okay, but I mean, this is in the so it's like a shockwave, big deal.
Yes.
So
right.
you get to see the underlying structure of space-time at the domain wall.
Right. And so my reasoning is it would act like a singularity.
I agree with that. Which, by the way, comes back to this has filled in more intuition behind the space tunnel.
Well, yeah, I mean, this is a space tunnel, right?
But doesn't necessarily have to have different dimension. I mean, this is one of a type of weird singularity that can exist in space-time that is not something, question. In the Einstein equations, are there solutions with variable cosmological constant? There must be.
Yeah, sure.
What about with discontinuous cosmological constant?
Not to my knowledge, for this reason.
Okay. Well, so, but you're just saying that. You're just saying that if I was solving the Navier-Stokes equations, and I had a discontinuity in, I don't know, pick your velocity, let's say, right? Then it doesn't obey the Navier-Stokes equations, and that's true. But the fluid still does something. In that particular case, it makes a shock.
Yes, right, which comes back to the point I was making last time of until we understand what the Rankine-Hugoniot conditions are for the Einstein field equations, we can't answer this question.
Okay, but let's look at that for a second, because what we've got here, maybe there's an energy argument that can be made here, because since we understand, okay, so one possibility is the causal edges have to go, so your argument might be the causal edges have to go somewhere. I'm not sure that argument is correct. I mean, there's no conservation of,
no, if it's a singularity, that's obviously not true.
It depends what kind of singularity it is.
Well, if it's a singularity that corresponds to a shock wave, then you get, in the space-time case, you get violation of global hyperbolicity, which effectively means you don't get local conservation of causal edges. In the same way as, you get a shock wave when you get intersection of characteristic lines in the case of fluid dynamics.
All right, so this is analogous to a fluid shock. And there is presumably no conservation of causal edges here. So the question is, what is there that can be measured across the shock. What is conserved across the shock? So an example of something conserved across the shock is, I mean, the spatial hypergraph. You can't just destroy elements in the spatial hypergraph willy-nilly. They can sit there and not update, but you can't really destroy them. So I kind of think there's going to be some conservation that, I mean, in a sense, causal edges are more fickle than spatial hypergraph edges, I might claim. The question is there a condition that can be got?
Yeah, I mean, it's the Rankine-Hugoniot conditions. So even though the causal edges aren't conserved, then you still get energy conservation and momentum conservation because effectively your 0 point for energy and momentum gets reset on the other side of the domain wall. Because you have a different vacuum state.
Well, okay, so the claim
which is what happens in fluid dynamics, right? It's what happens when you get intersection of characteristic lines that causes the the Cauchy problem to fail to be well posed.
All right, so energy momentum still conserved because the 0 changed across. Okay, let me remind myself how that works in a fluid shock. So in a fluid shock, you have different density on the two sides of the shock, right? I think that's right.
Yeah.
And
but
wow.
rho 1, rho 2, rho 1, rho 1, rho 1 U1 equals rho 2 U2.
Yes. Wow,
right.
That's really analogous.
Yeah, exactly. It's the same problem. It's the causal edges define the characteristic lines in the causal graph. That's the whole point. So intersection of characteristic lines corresponds to non-conservation of causal edges, which is the failure of the problem to be well posed.
Well, okay, so let's just look here. Let's look at this case, okay, the fluid case. That is a statement of momentum conservation, right? That equality.
No, that's a statement of mass conservation.
Oh, because
rho 1 U1 squared plus P1 equals rho 2 U2 squared plus P2 would be the statement of momentum conservation.
All right, okay. So mass conservation for a fluid. Okay, what is the analogous statement for us? Is it some statement about
energy conservation?
Well, but look, what we're trying to derive, what were we trying to derive? We're trying to, yeah, I'm not sure.
Right. I mean, it's saying that each causal edge has an associated energy along with it, but that energy can change on the two sides. The energy density for associated with each causal edge can change on either side of the domain wall. So the fact that you have intersection of your characteristic lines doesn't affect the energy conservation as long as it's subjected to this constraint.
No, but you're saying the interpretation of energy, each causal edge, you have a certain bundle of causal edges.
Each causal edge has an associated energy density that's computed relative to the underlying vacuum. So if you have two different vacua, that associated energy density is different.
Yeah, but it's also a question what the denominator of the density is, because that depends on the structure of space.
Right. Well, yeah. I mean, both terms are different, which is why you can potentially get satisfaction of some Rankine-Hugoniot condition.
Fair enough. All right, we've got a couple of things here, and then we're going to go look for black holes, because that was our original objective here.
Right.
If negative mass is a reduction of causal edges in a clean vacuum, doesn't that imply that there would be a limit on the amount of negative mass you could have? Yes, it absolutely does. Yes, it does. Because you can't have less than 0 causal edges, but you got a long way to go. If our current mass is 1 part in 10 to the 121, then there's a lot of negative mass you could get. But yes, it does imply that. It's a question for Richard here. Could the density flux at the limit be continuous? I'm not sure which limit we're talking about here. All right, let's go search for some black holes. Okay, you had sent through, Jonathan, ages ago here, oh boy, where is it? Gosh, this is the problem with my complexity of my life. Do you know roughly when you sent this? Here, I'll search for it.
It was about 5 hours ago.
Black hole detector van. Okay,
yes.
I see it here.
Yes, complete with Monty Python reference.
What on earth is that? Is that an actual Monty Python
Yeah, it was. They have a sketch about the cat detector van.
Oh, which goes in. Okay.
Never mind.
All right. Okay. See, I bet people on this live stream don't know, and people who don't come from a country with a national broadcasting network don't even know what things like television detector vans. Do they still exist? They cannot still exist.
I haven't seen one. I only know about it from that sketch.
Oh, you haven't seen one in real life?
I don't think so, no.
Okay, so for those people who might be curious on the live stream, you know, the BBC, right, it's a government-funded thing. And back when I was a kid, at least there used to be BBC One, and they very proudly introduced BBC Two as another television channel. And it was funded by a television license fee. And so the question was, could people have illegitimate televisions that were not licensed televisions? And the way that the government tried to enforce that is they had television detector vans that drove around neighborhoods trying to search for, I guess, what are these super heterodyne receivers or something, which have some additional, that essentially are generating something at some part of the carrier frequency. And so you could detect the presence of a television by this means, and then try and get people to pay their television license fees. So that's, but we're not doing the same thing for black holes, so don't get confused about that. There's no black hole license fees or anything. Okay. So last time we were looking at the question of causal connections. All right. So then you've got this, and you're asking the question: get causal connections. So this is showing which nodes in here are connected and which are not. So let's pull this over here. Actually, I want to make sure this is saved in the right place. And it's going to save in the wrong place unless I do the right thing here. Okay. All right. So now, what's get event horizons? Okay, well, let's try to understand this.
So, yeah, okay. So, do you want me to explain, or?
Yes. I mean, since you wrote the code.
Sure. Okay. So, okay. Basically, all it's doing is it's copying over a bunch of the causal invariance testing stuff we have for the multi-way evolution graph, but applying it to the substitution system and Wolfram model causal graphs.
Okay. So this is asking the question. What we're trying to do is make the causal edge map.
Yes, right. So what we're doing is we're computing the analog of a branch pair is an elementary light cone, i.e. it's an elementary bifurcation in the causal network. So we can then determine the analog of causal invariance, which is causal connection. So that's what causally connected Q is determining. And then get causal connections gives you the analog of the resolved and unresolved branch pairs, i.e. it's the elementary light cones where the two ends of the light cone end up being causally connected or causally disconnected.
Okay, so then we should be able to get the analog of the branch hill graph here, which is the connected piece of this, right?
Yeah, right. Connected.
Okay, so that is the branchial graph for a piece of this system. So what that's telling us is that the disconnection of this branchial graph is a sign of disconnection here, right?
Mm-hmm.
Okay, so let's try running this. Let's try running it a few more steps. Oh boy. The fact that even that takes a long time is kind of scary. Okay, so this space is a very broken up space. That's what's being said here.
Right.
This thing is like a bunch of black holes or something.
Mm-hmm.
Okay.
Right. So then get event horizon. Okay, in the case where get causally connected Q returns false, get event horizon will return the elementary light cone, the specification of the elementary light cone that causes the causal connection to fail.
Okay. So if I say in here, get event horizon.
Mm-hmm.
Whoops.
Horizons.
Why is it taking so compare? Okay, so those are the places where it first splits.
Right.
So if I were to do up here, I don't know what the 3,4 is. Oh, I see. That's doing that. Okay.
Yeah, that's just me getting out the elementary light cones.
Okay, so let's go here and put the get. So first thing we want to do is this. Let's just do 6 here.
You may want to flatten that, maybe. I don't know. Or not.
I see what you're saying. Well, actually, what I really want is to put different colors on each of the things that I want to put random colors on the two edges. So
does
really
highlight graph do that automatically? I don't know.
Not to pairs, it doesn't.
Oh, okay.
So I mean, what we want to do here, I think, is to say, well, okay, let me just do a flatten for now. Okay, so that's only showing 2 branch points. Why doesn't it show that branch point there?
Because we haven't evolved it long enough.
Okay. So do we need to evolve only the event horizons longer, or do we want to evolve?
You can just evolve the event horizons longer.
So in other words, this is trying to figure out whether these things will get connected.
Yeah, right. So obviously, as with causal invariance testing and all of that, this is a heuristic method.
Yeah.
But it's
so how far does it go?
So it goes. I think right now it goes. Okay. The basic way it works is it will look for all of the. It will look at all of the disconnected components up to 1/2 of the time step, and then determine which ones have then become causally connected at the time step.
Okay. Okay. Okay, so let's look here. Let's just go a little bit further here. Okay, what are we seeing here? So here we're seeing the branch points. This is labeling the branch points. Okay, I mean, I think this is doing the right thing. Now, to what extent are these like black holes, and to what extent are they more like cosmological event horizons?
Yeah, right. So what's going to happen is that this code should detect both, but the cosmological ones, you'll have both elements of the light cone are, one is on the interior, one is on the exterior. In the black hole case, you should get one on the interior and one on the horizon. And similarly, I think you should also get one on the horizon, one on the exterior.
So we got to go look for these things. Okay, so
yep.
let's. By the way, we had SWSH on our live stream is sending us a
variable dimensional fractal curve.
Yeah, let's take a look. Wow, okay. Well, that's interesting. See, unfortunately, the relationship between fractal dimension and graph dimension is a little bit funky. I mean, that is an interesting object. I mean, what we really would like is a graph whose limiting, which we can generate where the limiting dimension. I mean, the most naive version of this is the thing I was starting to draw before. The most naive version is, I think we have Max finally back, so maybe Max is really good at generating these things quickly. You know, the most naive thing I can imagine is something where it's a grid graph. Let me just find out what the vertex labels are here. Okay, 91 through 100. How do we do this graph union? Just takes some graph union just takes yeah. So what we want to then do is we want to say path graph and we could say in an incredibly hacky way table, well, let's just do table 100 to 110. What? Isn't that a path graph? What's, oh, I mean range. Okay, so that will be an example of a trivial sort of variable dimensional graph.
Right. I mean, a less trivial case would obviously be one in which the average vertex degree varies smoothly from one place in the graph to another.
Yes, but can we generate that?
Sure.
How?
By starting from a graph of homogeneous vertex degree and then defining a scalar field on top of it and adding or subtracting from the vertex degrees according to that scalar field.
I'm not sure that's going to be enough. Because I don't think that's what we did before with meshing, and it wasn't enough to change the dimension. Just filling in a bunch of extra edges here isn't going to change the dimension.
No, obviously the scalar field has to have, it has to be very smooth. It has to have, you know, very low derivative.
Is that going to be enough? Because you actually have to change the you know, progressive ball type structure. And I think this is a, look, as a matter of fact, we should add this as to our list, which we should be making of just straight mathy problems that somebody needs to solve. This is, so for folks on our live stream, somebody go solve this one. You know, construct a graph where the geodesic balls in the graph you know, where, I mean, it's clearly possible.
Yeah, but I still don't understand. Why wouldn't my approach not work? We know that the dimension is bounded above by the vertex degree. So if the vertex degree varies smoothly in accordance with a scalar field with derivative close to 0, the dimension should change.
Why? Hold on a second. The vertex degree.
Yeah, is an upper bound for the dimension.
If it's a uniform vertex degree.
Yes. So now if I have two regions of the graph where one has higher vertex degree than the other, then as long as it's sufficiently well connected, they will have different dimensions. So if you construct a graph with homogeneous vertex degree, then define a scalar field with low derivative on it, and
There's
then add and subtract
vertex degree. I mean, it's a different thing because you've got. Look, I can put extra edges in here, right, without affecting dimension.
No, of course. That's why I said upper bound.
Okay, but how does the upper bound on its
own? I mean,
help?
so you can't construct a four-dimensional network if it's trivalent, right?
Is that true? I don't think that's true. I don't think that's true. I think you don't have a problem doing that. It just has a different coefficient. I mean, it's just like in the NKS book, I certainly have examples. Look, for instance,
of trivalent networks in 1, 2, and 3 dimensions, but none in 4.
It is certainly not obvious to me that you can't do it in 4. I mean, in other words, because all that has to happen, no, I simply don't believe that. I'm sorry. I think that because I can take any four-dimensional network. Look, I can take a four-dimensional grid graph. Okay. Here. Okay. And every one of these nodes, I can simply split it into trivalent pieces. That doesn't change the overall dimension.
You mean into a trivalent cycle?
I've got a node here with, 4 edges coming out of it, right? Or 4 edges coming out of it.
Mm-hmm.
Okay, so all I'm saying is split that node
into a cycle of 3 vertices.
Yeah, that's fine, right? And then I've got trivalent. I've got something locally trivalent, but still happily globally dimension 4. I think it's more subtle than this. I think getting a thing that has, I think the local microstructure is actually very independent of the global dimension. Anyway, let's keep going for black hole searching. But, this is we need this. We need an example of this. There's got to be a better example than this crazy tadpole creature here. I mean, this tadpole is an example, just not a very exciting one, where actually, I mean, here's a question. If you look at that dimension-changing region, okay, you imagine a causal graph associated with this. Okay, I have to try something. Oh gosh, we got to make this a directed network and all kinds of things. What I wanted to do is to actually evolve this using some rule and see the thing kind of lose its dimensionality, right? What's going to happen is, actually, this is a good example because this is going to have dimension waves in it. Look, because what's going to happen here is this. So for every, I wonder if Max is here, maybe he could actually join us.
He just got granted moderator privileges on Twitch chat.
Well, okay, but can he? So what we need here is we need this. We need two-way edges on each of these, and then we need to just apply Wolfram Model to this for some random for some random rule, and basically see how these two. What's going to happen is the dimension is eventually going to equilibrate, so to speak. Are we going to hear Max in audio, so to speak?
Let me see. I tried to reach him on Twitch. Let me see if I can reach him on Rocket Chat.
Oh no, Devin sent him stuff.
Oh, okay.
Okay, well, he's going to be with us soon. Okay, all right, let's go back to black hole searching, and then we'll come back to dimension change. Yeah. Okay, so last time we had gone through and done some investigation of this, right? We looked at a particular set of, let me just pull it up here. Where did it go? Oh, that was black holes 02. Black holes 01 was what we looked at previously. We got this. And we've been looking at, gosh, we had a lot of these here. So this was our dendrograms. What were we looking at here? We were looking at different components. Okay, so what we want to draw are these these things here, right? So help me draw one of those for with your, and then we had done that.
I mean, why? The reason for constructing these elementary light cones was so that we don't have to draw these.
Okay. All right, well, let's do the corresponding picture here that we had done for this with your thing, okay? So we've got this both for this case and for the Wolfram model case. We're looking at all possible rules. All right, we'll look at that in a minute. Let's first of all look at this. Okay, so what you're saying, we're not looking at a causal connection graph. What are we looking at here? We're looking at this thing here, the causal connections, this causal connections list thing. Is that correct?
Right. I mean, the point of this function is to summarize all of the information we could want from the causal connectivity graph.
So you're claiming, okay, well, let's just do a brute force thing here, okay? So for each, all right, we'll just do ABA here if you want. For each one, we get this. Actually, what we really want to do here is that thing, and it's this is the causal connection graph there. Oh, we don't need this, right? We just need the rule, correct?
Yeah, right. Well, and the initial condition and the step number.
What's that 3 doing there? I think that was a thing to do with. All right, let's try running this.
That won't work.
Okay, what's wrong with it?
Well, get causal connections list returns an association.
Ah, so I want to say connected here.
Right.
Okay. Oh, I gotta warm up the machines. You know, it's just amazing that in the modern world, you can't launch processes on all these machines instantaneously. It's kind of a not our fault situation, but it's all the SSH authentication stuff happening and all kinds of other weird things. It's a shame I had another machine here. What? How could that work? How could that be the case? Look at that. Received only 31 of 32 connections from some subkernel somewhere. It's crazy.
I'm trying to remember the last time you called parallel map monitored and it worked correctly. I think it was a while ago.
Well, what is all this junk? Is that going to happen for, wait a minute, something has gone wrong. Is there any evidence that this is working at all? I think we've got some more serious problem here. Oh. Well, what's it doing here? Something is going wrong here. So, but we clearly have some.
Wait, vertex. Hang on. Can I see the line of code again?
That looks awfully like it's a piece of your code.
Yeah, except it doesn't, because I don't. At no point do I refer to index graphs. So can I see again?
What the input was?
Yeah, can I see the line?
That's a lot of messages from 100 computers. Oh, for goodness sake. Arg! Okay. Well,
yeah, I mean, my confusion is that my code doesn't make any use of index graph or vertex delete.
okay, well, let's do this. Let's say take this comma 5, for example. Okay, so something is clearly going very wrong here. All right, so let's first of all, let's pull up these. Okay, hunky-dory. Now let's just do this for the first one of those. Okay, you are implicated.
Hang on, what is going wrong here?
Hey, Max, are you here now?
Yes.
Hello there. Okay. Did you hear what we were trying to do earlier?
Yeah. Are you talking about the mixed dimensionality graph?
Yes. So the question here, well, Jonathan tries to debug that thing. The question here is this. First question is, can you see how to construct such a graph? The second question is just to take this tadpole creature and to try and evolve from that with Wolfram Model with some simple rule and just see the thing equilibrate.
Yeah, I can try something.
I mean, here, we should be able to just do this by making a two-way graph. So every edge here, I mean, I guess if I just say edge list of this, and then take, let's see, what I want to do is say directed graph. Of that. And then what I want to do here is I want to say join hash and reverse slash at hash this and then graph of that, and that should make every edge be two-way. Do you agree? Looks like it. Is it making it three-way? Why did it just make it
four-way?
Why?
Is it because when you make a directed graph? Oh, hold on.
Yeah, Max is right. Is a directed graph of an undirected graph
Might just do the
two
right
edges.
thing.
Produces two edges,
Yeah,
I think.
All right, okay, so you're saying that just does the right thing. Oh yeah, you're right. System is smarter than we were. Okay, so then we take this tadpole and we're going to evolve from this tadpole. And if we just say, well, we could just use our sort of standard rule, although we might want to use a simpler one. Let me just pull it up here. Actually, I can just do this, I hope. And we should just be able to take this thing, if I'm not mistaken, and take edge list of that. And then I think we have to say list triple at this, is that correct? What is it called? Oh, plots
list.
State plots list.
No, states plots list.
Like that?
Yeah.
How much of a mess is this going to make? Wow. Let me enter. Oh, just finished. Well, the tadpole is turning into a frog very rapidly. Or is it? No, the tadpole
looks
still
like
has
it's
a tail now.
eating the tail.
What's that? Yeah, it's eating.
Looks like it's eating the tail, but you should involve it a bit longer to see if it does it completely or not.
It'll eat the tail. I mean, if we take one of these,
I mean, I'm just afraid it could be layout issue. Also, it doesn't look
really
like it.
eating the tail. I think it's just, look, I think what's going to happen is the tail is going to be gradually expanded, and you're going to end up with a thing that is, I mean, it is a weird thing because this has a lot of internal structure here. Oh boy, this is getting big now. Well, we could try a smaller case. We'll just try 5.5 and just put its tail on element 25. Let's give it a longer tail. And let's only evolve for like 3 steps. Okay, so let's take those guys. And then let's here go graph 3D, rule at hash. I wish we had, and by the way, Max, in terms of your things to be doing, the 3D version of Wolfram Model plot would be really good to have.
Yeah, I agree.
Okay, so it's turned into some kind of weird mace-like thing here. So it's still pretty flat.
It's kind of like a spatula.
I suppose. Yeah, it's an eating utensil of some kind or something, or whatever. Well, okay, so what's going to happen to this? So this is presumably, I mean, what's interesting about this is if we measure its dimension now, we will find its dimension is different in different places. So this is developing an intrinsic dimension associated with this. So I think an interesting thing to do would be to use one of those knitting rules on here. But let's try running this a little bit longer. Because the question is this dimension, here, let me pull that out for another notebook here. Now this is where I want to go into VR. I do have my VR system set up. I could take this. Okay, so this is, so the question now is, if we start measuring dimension of this thing, what we're basically going to find is that within the sort of the substructure here, it's going to have its 2.7 dimensional thing, but then the overall dimension as we go to larger scales is going to look 2-dimensional. And if we go to in this region, it's going to look 1-dimensional here. So it's going to be, for small values of R, it's going to look 2.7 dimensional, and for larger values of R, it's going to look either 2-dimensional or 1-dimensional. So the real question is, can we invent a graph where kind of, what is the analog of a grid graph which continuously, well, look, the geodesic ball on the grid graph clearly just yeah, I'm not sure. I mean, it would be nice to be able to have something where it's a grid graph where you can continuously vary its dimension, but I have no idea how to do that. No idea. Because, you know, contrary to what Jonathan was saying, I mean, the dimension. Yeah, I mean, you can change a Cantor set's dimension, for example, by just filling in different fractions of the middle third, so to speak. All right, anyway, let's go back to the black hole searching. Okay, so what we've got here, so Jonathan, did you find the bug?
Yeah, like I said, it's not a bug in my code.
What is it?
It's a bug in substitution system causal graph, where if you give it an initial condition that doesn't, I mean, in this case, for instance, the initial condition clearly doesn't match the rule, so it doesn't evolve, and substitution system causal graph returns this error.
Oh, well, so let's report that. Jan can work on fixing that. Okay, fine. So then that should work.
Yep.
Okay. All right, then here we go. Okay, so should we actually draw? Oh, I see. There's just the first 5. Should we draw the causal graph together with the actual? I think we want to draw the causal graph together with this causal connections thing. Do you agree?
Yeah. Okay. Sure. That could be interesting.
So.
But I think it's also useful, to, as I say, to actually plot the event horizons, given that that's what we want to find.
And how would we do that here?
Get event horizons, and then do a highlight graph.
But then we want to highlight this graph.
Oh, you want to highlight the causal connections graph. I was thinking just plot the causal graph and highlight the event horizons, but I mean, we could also do it that way.
Fine. Well, either way, we can plot the causal graph. Okay, so this gives us these branchial graphs, which should be a map of the different causally connected regions, correct?
Yes, something like that, yeah.
Right, so this, for example, here might be a black hole type thing.
Right, but they're only causally, in the same way as you keep reminding me, the branchial graphs are kind of only branchially connected at one level. These are only causally connected at one level.
Okay, so if it hits the actual moment of event horizon, this will be an indicator.
Right. That it is disconnected here is a necessary but not sufficient condition for being event horizon.
Right. So what we really want is the whole family of these. What we really want is the sort of causal, not branchial graph, but we want the thickened branchial graph.
Right. I mean, it's actually just a space. It's one representation of a space like hypersurface. That's a non-hypergraph representation.
Well, it's a projection backwards in the spatial, in this causal graph. I think we understand what it is. I mean, you're going backwards. Okay. So let's all right. Okay, well, you're suggesting that we just plot these things here to begin with.
Yeah, why not?
Okay, fine. We can do that. Although I would prefer to, how do we make bigger? Do you have any idea how to highlight the graph? Let's say if we just say large, does that do anything useful?
It might be vertex size large. I forget how that works. There we go.
Well, that wasn't useful.
Maybe not. Does style take a size? It does, doesn't it?
Well, actually, this
there you go.
Something. Let's see what happens if I say scaled of 0.05. Is that useful? Okay, it's a little bit crazy because it has those, but that's okay. And now we probably want to do layered graph plots here. Do you agree?
Yeah.
I'm going to make these 6 for the time being. And should they both be 6, or should the event horizons have a different value?
Probably the event horizon should be larger than the actual causal graph. So you could have one as 6 and one as 4 or something. I don't know.
Let's have 5 and 7, let's say. Okay, now let's put a time constraint around this. Time constraint, let's say, I don't know, 5 seconds or something. And let's also put here, image size, arrow, I don't know, 150 maybe. Just see what that produces. Those arrows are ridiculously big. Max, do you have any comment on that?
Not really. I mean, I think it's just a default graph.
Arg, why is it doing that? But where's vertex style? Oh, come on. Why is it doing that? I don't understand.
As I was saying, aren't you meant to wrap the thing in a style?
I see, okay. So you're saying here, style, let's have green be the color of event horizons. Okay.
A little sickly.
Yeah, well. All right, okay. We have at least a somewhat approach here. Okay, time constraint 5. All right, let's go ahead then and map this across all
In fact,
rules.
Inadvertently, this is a really good illustration of what I was saying before about the distinction between cosmic and black hole event horizons. So like on the left there, you see that's an example of a black hole event horizon because there's a bunch of stuff going into that point at the bottom, but none coming out. And so there you see that there are 2 light cones, one connecting the boundary to the exterior and one connecting the boundary to the interior.
I need to see it in a bigger picture. Let's make a bigger picture here. Okay, explain it again.
Right. So you see on the left there that this is an example of a black hole event horizon because there are causal edges going in from into that prong.
Into this prong here.
No. The prong just next to it.
This one.
You see, there's. So, if you look at the bottom level, the 5th event from the left.
Yes.
Right. That's something where we have 2 causal edges going in, and none coming out.
Yes.
Right. And so you can see there that you have 2 elementary, unlike in the cosmological case where you'd get just one event horizon, one light cone corresponding to the event horizon. Here we have 2, one that's connecting the one on each side, so to speak.
I'm sorry, I'm not quite understanding. Which part of this picture do you claim is a black hole like event horizon?
Well, that one there, yeah, the 5th. I mean, it's the most black holey of any.
Because it has edges coming into it from random places, you're saying.
Right. I mean, it's not a particularly convincing one because they're not coming in a time extended way.
Okay, fine. That's what I was confused by. Okay.
Right.
Okay. All right. So let's try doing this. This. Parallel map monitored of that whole thing onto this. All right. Let us try. Oh, well, that was stupid. Well, what just happened here? Hash? Oh, silly me.
You didn't, the plot.
Oh, come on.
Well, ABA is not going to be a valid initial condition.
Oh, well, that's because I got different initial condition for the two cases. Okay, and I need another fix here. Okay, all right, so these, what's that?
That's the one second row, second from the right. That's an interesting one.
Yes. But no event horizons.
Right.
Okay, so there are some event horizons there, according to you. This one looks interesting to me. Okay, what does this guy do? That's a very minimal case.
Yeah, that's not it's not super interesting.
Well, what is it really doing? Why is it attributing? So that's an event horizon because it is a branch point where the things that go through that branch point never intersect with the things that go through another branch point, right?
Right.
But in your notion of an event horizon, so what we really need to do is to connect, any event horizon here is actually a pair of things, right?
Right. You have an interior and an exterior.
So I think we need to connect those in these pictures. We need to just draw an edge from one to the other.
Or at the very least, we should highlight each element of the elementary light cone in the same color.
Well, you mean, but this is the tip of the elementary light cone, and so now the question is, what are the sub? What's the subgraph? What's the neighborhood graph underneath that?
Mm-hmm.
Okay. Well, which are we going to do here? So let's at least look for. Yeah, I mean, because something like this is just completely confusing. What's going on? I have no idea what's going on there. So, well, you're saying that the event horizon should have under it each sort of seed of event horizon should have an elementary light cone underneath it.
Right, right.
And the event horizon is the distinction between the successors of those two seeds.
Well, it's just that it's the distinction between those two seeds, right? What one half of the light cone is on the interior and one half is on the exterior.
So you're claiming they will be disjoint, but they would have the same color. If we look at the light cones that go underneath this.
Yeah.
That one looks like it might be promising. Why are there only three? I don't understand, because one of them is a shared one somewhere.
Yes, right. So it looks to me like, yeah, the middle vertex might be shared between the two.
Which is going to look very complicated in terms of our...
Oh, no, actually, I think it's the vertex on the left that's shared. I don't know.
Okay, but fine. But so
we need to figure it out.
One thing we could do here, let's do the following. The simplest thing we can do is to turn the event horizon into, instead of flattening the event horizons, we can make them be path graphs, right?
Right. But that's going to try and highlight something that doesn't exist.
What do you mean? No, I'm saying we're highlighting, we're putting in green a graph that connects the two edges of the event horizon, which is a fake graph.
Right, I understand. But so does highlight graph work if you pass it a subgraph that isn't actually a subgraph of the graph in the first argument?
I don't know. We're about to find out.
I doubt it.
Okay, well, so then we want to add to the...
So we want to add we want to add an edge, basically.
Well, let's just try this. Yeah, so we need to add an edge. So to this, we need to take event horizons and we need to say, before we do the highlight graph, I mean, actually, we could just forget the highlight graph. We could just add to the graph. How do you do that? You just say graph union, right?
Right. Graph union with path graph.
Okay, let's just do that.
John, can you explain why the third one on the second row doesn't have a black hole in it?
Yeah, that's what I'm trying to work out, because yeah, you're right. That's a black hole event horizon rather than a cosmic one, and it's not picked up by the heuristic, which means either the heuristic is wrong or we didn't run it long enough.
Okay, hold on. Let's just try and do this here. So we want to add to this a path graph. So we want to say graph union, if I'm not mistaken. Of this with this graph union varogs.
Union is, so I would have thought graph union should be. Yeah, it is.
Okay, and now here on the path graph, we have to say edge style arrow green, vertex style arrow green, vertex size arrow scale to 0.05. All right, are we really going to run the whole thing? It's a graph union of that. Can you see if this code is right?
As long as graph union preserves styles, I don't see any reason why that would fail.
Something's wrong here. That's time constrained.
Oh yeah, there's a stray bracket.
Where?
Well, time constrained, presumably the time constrained is the 5.
That's wrong. Okay, that's the graph union.
Yeah, so just remove that bracket.
Oh gosh, this is my problem with the. Oh, when you have 100 machines, they don't stop. Okay, what did I do wrong here? Slot number 1 cannot be filled from graph union resource function, blah, blah, blah. Oh, look at this. See, that is the.
You need 2 maps.
Well, in particular, I need that thing there to close with a function and to say function ru. Oh, gosh, this is painful. Wow. Oh. Okay, exterminate all of these poor kernels. Okay, let's try it again. I have to rerun your code here. All right, let's try it again. We'll have to relaunch the machines. Okay. Oh, come on. Graph union called with one argument. Oh, I see, because there are no event horizons, but graph union should work with one frigging argument. That is a bug. Can we report that, please? Do I need to report that? Okay, that's really stupid. So let me just report that bug. Apparently nobody else can do it. It's really weird, actually, that it fails. Let's just check it's really true. Dumb. Okay, so it's saying graph union of, let's say, grid graph 3, 3. That's just crazy. All right. So we have to put some special thing in there. How do we do this? You guys still there?
Yeah.
Okay.
Just define your own graph union, which should take care of that case.
Well, here. This is a total hack. What? Oh, those were the unions. Those were the graph unions.
Yeah, so as I say, yeah, graph union doesn't preserve styles.
Okay, this requires a little bit more work. But so let's just zoom out for a second to understand what we're achieving here. We should probably wrap in a minute. But
yeah, I actually have to go in a second.
Okay. Well, fine. Let's wrap it up, and we'll have to continue. But just to understand back from what we have done before we messed it up completely here. These results here, right, are showing a variety of event horizons where we really want to. I mean, the thing we really want to do is connect the two sides of the horizon. Connect the sort of the bifurcation that makes the horizon, and then color the light cones beneath each side of the horizon. Right?
Right.
And then what we're expecting is to see, yeah, we're just going to have to go on with this. I mean, this is, let's see, when are we going to go on with this? Might have a chance even tomorrow. Got a couple of other, yeah, well, let's see if we can't go on with this in the later end of tomorrow, if that works. Right, we got one last question here. Maybe we can try and, someone's asking, what's the white hole version of Hawking radiation? What is the white hole version of
Hawking absorption?
Yeah, well, that's what the time reverse thing should be. But what it must be then is a place where it is doing anti-thermodynamic things, whereas Hawking radiation is making sort of thermodynamic stuff out of a black hole, right? The Hawking radiation of a white hole must be essentially a black hole refrigerator that's sucking entropy out of the outside world, I think. There's a question about space-time emerging from these graphs. No, not these graphs. More complicated story. Check out the whole description of the visual summary of the this is a good place to get a sense of what's going on. That's the spatial hypergraph. That's where we think space comes out. These things that we're looking at right now are causal graphs down over in this corner. Okay, wait a minute. If you invert the multi-way causal graph, the black holes will turn into white holes and vice versa. Makes me think the Wick rotation is the same as this inversion, and that local inversions may happen all the time, but not global inversions. Let's see, at least not until you consider Penrose's CCC conditions for an entropy dip at cosmological scales. Because it's so empty, it acts quantum. Global becomes local over 10 to the 100 years. I don't completely understand that, although I think it is correct that what we identified as being CPT transformations in the multi-way causal graph would turn black holes into white holes. And yeah, I mean, the existence of like black hole, white hole, sort of virtual black hole, white hole pairs seems likely, but we just don't quite yet understand that. And we probably will understand it when we get these pictures to actually work properly. All right, so should we wrap up here and continue at another point? If Jonathan has to go, I think that's, I'm supposed to go off and do something else here too. But this is very addictive, so I'm have a habit of just keeping on going with this. So okay, fine. Let's wrap up the let's wrap this up. So thanks to everybody who joined us here, and we will be continuing tomorrow. We have some live streams that are about my day job that may be of interest to different crowd. Where we're doing software design, and then we hopefully late tomorrow afternoon, at least Eastern time, we might be able to try and continue to look for some black holes. And then on Thursday, we're back to looking at Bell's inequalities. So let's wrap this up for now then. Okay, thanks all.